we will learn about the parameter estimation and hypothesis test to do some statistical inference. Statistical inference is the process of using a sample to make inferences about the population. Why we use sample instead of population? Because of time, cost, and other considerations, data often can't be collected from every element of the population. In such cases, a subset of the population called the samples is used to provide the data. Data from the sample are then used to develop estimates of the characteristics of the larger population. Characteristics such as mean, variance, and so on are what we call the parameters. The process of using sample data to estimate the parameters of the selected distribution is what we call parameter estimation. Next, we will learn some methods of parameter estimation. Maximum likelihood estimation, MLE, is a technique used for estimating the parameters of a given distribution using some observed data. For example, if a population is known to follow a normal distribution but the mean and variance are unknown, MLE can be used to estimate them using a limited sample of the population by finding particular values of the mean and variance, so that the observation is the most likely result to have occurred. The notion of the likelihood as a basic measure of the quality of a set of predictions for observed data. Here, we show how MLE works. Let X be the observations from n dependent and identically distributed random variables drawn from the probability distribution F, depending on the parameter theta. For example, probability distribution could be the normal distributions, which depend on the parameter standard deviation and the mean. The purpose of MLE is to maximize the likelihood shown here. We can also maximize the log likelihood in this way to get the same result, since the logarithm function itself is a continuous, strictly increasing function over the range of the likelihood. On this page, we will learn about the expectation maximization algorithm, EM algorithm. As the saying from the pattern recognition and the machine learning goes, a general technique for finding maximum likelihood estimators in latent variable models is the expectation maximization algorithm, EM algorithm. The latent variable is the variable that is inferred using the models from the observed data. We show the maximum likelihood estimation in the presence of latent variables in a mathematical way. Let the X be the observed data, Y be the latent incomplete data, and the Z be the complete data. And the data likelihood is defined over here. This is the likelihood of the random variable Z given theta. It is equal to the function of the latent variable Y and parameter theta times the function of parameter theta. Suppose we have the complete dataset Z and observe the data X and latent Y. Then we calculate the data likelihood which mentioned in the previous page. Then we can use the EN algorithm to perform the maximized likelihood estimation. The EN algorithm is an iterative approach that cycles between two modes. The first mode attempts to estimate the missing or latent variables, called the estimation step or E-step. We can see the formulas to define the conditional expectation of log likelihood of the complete data Z based on the parameters lambda. The second mode attempts to maximize the parameters of the model in the presence of the data, called the maximization step or N-step. The formula is shown here. The EN algorithm can be applied quite widely. Also, it is perhaps most well-known in machine learning for solving the unsupervised learning problems, such as clustering. After we finish the parameter estimation, then we come to the new part, hypothesis test. A hypothesis test is also a form of statistical inference that uses data from a sample to conclude a parameter or the probability distribution. We have the formal procedure to test the predictions, including the 5 main steps. First, we need to state the research hypothesis as a known and alternate hypothesis. The known hypothesis is always the accepted fact in the question, and the alternate is the opposite of what is stated in the known hypothesis. The second step is to collect the data in a way designed to test the hypothesis. The third step is to perform an appropriate statistical test. The next step is to decide whether the known hypothesis is rejected or suggested. The final step is to present the findings in the results and the discussion section. Following, we will explain the third step to perform an appropriate statistical test in more detail. The third step is to find the appropriate test statistics. A test statistics describes how closely the observed data matches the distribution expected under the known hypothesis of that statistical test. The test statistics is used to calculate the p-value of the results, helping to decide whether to reject the known hypothesis. There are several types of test statistics. Different statistical tests predict different types of distributions. So, it is important to choose the right statistical test for the hypothesis. In most cases, we use the Z-test often. A Z-test is used to determine whether the means of two groups are different when the variance are known and the sample size is large. P-value stands for conditional probability value, which is the probability of getting a test statistic at least as strong as the one given known hypothesis was true. As shown in this graph, this is the two-tailed test. It means that if the result falls in the area in the middle of the distribution, the null hypothesis H0 is suggested. Otherwise, the blue rejection region in both tails is to reject the null hypothesis H0. The significance level is denoted by the Greek letter alpha, usually 0.05. The fate of the null hypothesis depends on the alpha. For instance, if the p-value is 0.03 and alpha is 0.05, we could reject the null hypothesis at a significance level of 0.05. However, if alpha is 0.01, then we would suggest the null hypothesis. Thus, we need to compare alpha with p-value. We can get the answers whether to reject the null hypothesis. We have an example of a z-test. First, we take a look at the question. Blood glucose levels for obese patients have a mean of 100 and SD standard deviation of 15. A researcher thinks that a diet high in raw cornstarch will have a positive or negative effect on blood glucose levels. A sample size N is 30 patients have tried the raw cornstarch diet, have a mean glucose level of 140. So we need to test the hypothesis that the raw cornstarch had an effect. At the first step, we state the null hypothesis is the accepted fact that the population mean is 100. We have a two-tailed test since the question indicating the mean is not equal to 100. If we have the mean is greater than 100, this would be the one-tailed test, since this is just going in one direction. Or if the mean is less than 100, that is also one-directional. Here we have a two-tailed test. The second step, the common choice for the level of the significance is alpha equals the 0.05. Thus, two areas add up to 5%, so we got half in one tail. In the step 3, what we want to do at this alpha level is to find this z-score, which is unknown, which we will get it later. This is our rejection region, and it is the right-hand part tells us the area from the mean to any this z-score. So one half of the bell curve is the 50%, and this little area is 2.5%. So, which means this area between the mean and the z-score must be the 47.5%. And we could look this up in the z-table in the next page. Actually, look up the decimal point 475. So the z-score at this boundary is 1.9 and 0.06. So we can get the z-score is 1.96. Because the curve is symmetrical, that also means this z-score is the 1.96 and the left side is negative 1.96. At the fourth step, we want to calculate the test statistics, and we want to find out if that test statistic falls into those two-tailed rejection region. If it does, we can reject the null hypothesis. How we do that is with a formula z equals to x bar is the mean minus mu of 0. It's the population mean, all over the standard deviation divided by the square root of our sample size. We are given all the information in the question. So it is basically just plug in and solve. At the final step, we got the 14.6. Take this value and we are going to see if it is going on a normal distribution curve like this, able to go away to the right, and which is in this rejection region. It is larger than the z-score, so we can reject the null hypothesis, which means our alternate hypothesis is now in place that the mean is not equal to 100. The purpose of taking a random sample from a lot or population and computing a statistic such as the mean from the data, is to approximate the mean of the population. How well the sample statistic estimates the underlying population value is always an issue. A confidence interval adjusts this issue because it provides a range of values that is likely to contain the population parameter of interest. The confidence interval Ci is the range of values that expect the estimate to fall between a certain percentage of the time if we sample the population in the same way. Confidence intervals are constructed at a confidence level, and it equals to 1 minus alpha. Normally, we set alpha as 0.05, thus the confidence level is 0.95. Oftentimes, what does this mean? It means that if the same population is sampled on numerous occasions and interval estimates are made on each occasion, the resulting intervals would bracket the true population parameter in approximately 95% of the cases. A confidence stated at 1 minus alpha level can be thought of as the inverse of a significance level alpha. In the following pages, we will learn about how to calculate the confidence interval. First, we need to check the sample size of the dataset. If data follows a normal distribution in a large sample size n greater than the 30, then use the z distributions to find the critical values like the z-score with population data. Otherwise, use the t distribution in a small dataset with sample data. Then we need to confirm the critical values like the z-score. It is the same as what we learned from the test statistics. In the same way, the statistic test can be one- or two-sided. Confidence intervals can also be one- or two-sided. A two-sided confidence interval brackets the population parameters from above and below. A one-sided confidence interval brackets the population parameter either from above or below and furnishes an upper or lower bound to its magnitude. Here we have the formulas for the sample deviation to refer to. Oftentimes we will get from the question directly. Since we get the basic on how to obtain the information including the z-score, the critical value of the z distribution by looking up the z-table. Also, the population mean, standard deviation, and sample size, so we can get the result of the confidence interval in this formula. If in the small sample size, we could use the t-score to replace the z-score. In real life, we replace the population values with sample values unless we do a complete synthesis. We could follow these formulas based on the sample mean and sample deviation are known. We have an example to calculate the confidence interval. In one survey, we have more than 30 observations following a normal distribution. Since the sample size is more than 30, we can use the z distribution in the population dataset for test statistics. Assuming it is a two-tailed 95% confidence interval. According to the lookup table for z distribution, alpha is equal to 0.025. The corresponding critical value z statistic is 1.96. Other values we could get from the questions. In this way, we can calculate the upper and lower bounds of the 95% confidence interval. This is the end of the probability and statistic part. Thank you for your time.